Hello, this is Colin Selleck, Binghamton University. This lecture is on instrument types and performance characteristics. Two of the important aspects of measurement that were covered in a previous lecture concerned how to choose appropriate instruments for a particular application and a review of the main applications of measurement. Both of these activities require knowledge of the characteristics of different classes of instruments, and in particular, how these different classes of instruments perform in different applications and operating environments. We will therefore start this lecture by reviewing the various classes of instruments that exist. We will see first of all that instruments can be divided between active and passive ones according to whether or not they have an energy source contained within them. The next distinction is between null-type instruments that require adjustment until a datum level is reached, and deflection-type instruments that give an output measurement in the form of either a deflection of a pointer against a scale or a numerical display. The third distinction covered is between analog and digital instruments, which differ according to whether the output varies continuously, that's analog, or in discrete steps, that's digital. Fourth, we shall look at the distinction between instruments that are merely indicators and those that have a signal output. Indicators give some visual or audio indication of the magnitude of the measured quantity and are commonly found in the process industries. Instruments with a signal output are commonly found as part of automatic control systems. The second part of the lecture looks at the various attributes of instruments that determine their performance and suitability for different measurement requirements and applications. We will look first at the static characteristics of instruments. These are their steady state attributes when the output measurement value has settled to a constant reading after any initial varying output. Examples are accuracy, measurement sensitivity, and resistance to errors caused by variations in their operating environment. We will then go on to look at the dynamic characteristics of instruments. This describes their behavior following the time that the measured quantity changes value up until the time when the output reading attains a steady value. Various kinds of dynamic behavior can be observed in different instruments, ranging from an output that varies slowly until it reaches a final constant value, to an output that oscillates about the final value until a steady reading is obtained. The dynamic characteristics are a very important factor in determining the suitability of an instrument for a particular measurement application. Instruments are divided into active or passive ones according to whether the instrument output is entirely produced by the quantity being measured, or whether the quantity being measured simply modulates the magnitude of some external power source. This is illustrated by examples. An example of a passive instrument is the pressure measuring device shown here. The pressure of the fluid is translated into a movement of a pointer against the scale. The energy expended in moving the pointer is derived entirely from the change in pressure measured. There are no other energy inputs into the system. An example of an active instrument is a float-type petrol tank level indicator as shown here. Here, the change in the petrol level moves a potentiometer arm, and the output signal consists of a proportion of the external voltage source applied across the two ends of the potentiometer. The energy in the output signal comes from the external power supply. The primary transducer float system is merely modulating the value of the voltage from this external power source. In active instruments, the external power source is usually in electric form, but in some cases it can be in other forms of energy such as pneumatic or hydraulic. One very important difference between active and passive instruments is the level of measurement resolution that can be obtained. With the simple pressure gauge, shown here, the amount of movement made by the pointer for a particular pressure change is closely defined by the nature of the instrument. While it is possible to increase measurement resolution by making the pointer longer, such that the pointer tip moves through a longer arc, the scope for such improvement is clearly restricted by the practical limit of how long the pointer can conveniently be. In an active instrument, however, adjustment of the magnitude of the external energy input allows much greater control over measurement resolution. While the scope for improving measurement resolution is much greater incidentally, it is not infinite because of limitations placed on the magnitude of the external energy input, in consideration of heating effects, and also for safety reasons. In terms of cost, passive instruments are normally of a more simple construction than active ones and are therefore cheaper to manufacture. Therefore, choice between active and passive instruments for a particular application involves carefully balancing the measurement resolution requirements against cost. The pressure gauge just mentioned, this one here, is a good example of a deflection type of instrument where the value of the quantity being measured is displayed in terms of the amount of movement of a pointer. An alternative type of pressure gauge is the dead weight gauge shown here, which is a null type instrument. Here, weights are placed on top of the piston until the Here, weights are put on the top of the piston until the downward force balances the fluid pressure. Weights are added until the piston reaches a datum level, known as the null point. Pressure measurement is made in terms of the value of the weights needed to reach this null position. The accuracy of these two pressure measuring instruments depends on different things. For the first one, it depends on the linearity and calibration of the spring, while for the second, it relies on the calibration of the weights. The calibration of weights is much easier than careful choice and calibration of a linear characteristic spring, which means that the second type of instrument, the null type, will normally be more accurate. This is in accordance with the general rule that null type instruments are more accurate than deflection types. In terms of usage, the deflection type instrument is clearly more convenient. It is far simpler to read the position of a pointer against a scale than to add and subtract weights until a null point is reached. A deflection type instrument is therefore the one that would normally be used in the workplace. However, for calibration duties, the null type instrument is preferable because of its superior accuracy. The extra effort required to use such an instrument is perfectly acceptable in this case because of the infrequent nature of calibration operations. An analog instrument gives an output that varies continuously as the quantity being measured changes. The output can have an infinite number of values within the range that the instrument is designed to measure. The deflection type of pressure gauge seen here is a good example of an analog instrument. As the input value changes, the pointer moves with a smooth, continuous motion. While the pointer can therefore be in an infinite number of positions within its range of motion, the number of different positions that the eye can discriminate between is strictly limited, this discrimination being dependent upon how large the scale is and how finely it's divided. A digital instrument has an output that varies in discrete steps and so can only have a finite number of values. The revolution counter shown here is an example of a digital instrument. A cam attached to the revolving body whose motion is being measured, and on each revolution the cam opens and closes the switch. The switching operations are counted by an electronic counter. The system can count only whole revolutions and cannot discriminate any motion that is less than a full revolution. The distinction between analog and digital instruments has become particularly important with the rapid growth in the application of microcomputers to automatic control systems. Any digital computer system, of which the microcomputer is just one example, performs its computations in digital form. An instrument whose output is in digital form is therefore particularly advantageous in such applications, as it can be interfaced directly to a control computer. Analog instruments must be interfaced to the microcomputer by an analog to digital converter, A to D converter, which converts the analog signal output from the instrument into an equivalent digital quantity that can be read into the computer. This conversion has several disadvantages. First, the A to D converter adds significant cost to the system. Second, a finite time is involved in the process of converting an analog signal into a digital quantity, and this time can be critical in the control of fast processes where the accuracy of control depends upon the speed of the controlling computer. Degrading the speed of operation on the control computer by imposing a requirement for A to D conversion thus impairs the accuracy by which the process is controlled. The final way in which instruments can be divided is between those that merely give an audio or visual indication of the magnitude of the physical quantity being measured, and those that give an output in the form of a measurement signal whose magnitude is proportional to the measured quantity. The class of indicating instruments normally includes all null-type instruments and most passive ones. Indicators can also be further divided into those that have an analog output and to those that have a digital display. A common analog indicator is the liquid in-glass thermometer. Another common indicating device, which exists in both analog and digital forms, is the bathroom scale, seen here. The older mechanical form of this is an analog type of instrument that gives an output consisting of a rotating pointer moving against the scale. More recent electronic forms of bathroom scales have a digital output consisting of numbers presented on an electronic display. One major drawback with indicating devices is that human intervention is required to read and record a measurement. This process is particularly prone to error in the case of analog output displays, although digital displays are not very prone to error unless the human reader is careless. Instruments that have a signal type output are commonly used as part of automatic control systems. In other circumstances, they can also be found in measurement systems where the output measurement signal is recorded in some way for later use. Usually, the measurement system involved is an electrical voltage, but it can take other forms in some signals, such as an electric current, an optical signal, or a pneumatic signal. Static characteristics of instruments. If we have a thermometer in a room and its reading shows a temperature of 20 C, then it does not really matter whether the true temperature of the room is 19.5 or 20.5 C. Such small variations around 20 C are too small to affect whether we feel warm enough or not. Our bodies cannot discriminate between such close levels of temperature, and therefore a thermometer with an inaccuracy of 0.5 C is perfectly adequate. If we had to measure the temperature of a certain chemical process, however, a variation of 0.5 C might have a significant effect on the rate of the reaction or even the products of a process. A measurement inaccuracy much less than 0.5 C is therefore clearly required. Accuracy of measurement is thus one consideration in the choice of instrument for a particular application. Other parameters such as sensitivity, linearity, and the reaction to ambient temperature changes are further considerations. These attributes are collectively known as the static characteristics of instruments and are given in the datasheet for a particular instrument. It is important to note that the values quoted for instrument characteristics in such a datasheet only apply when the instrument is used under specified standard calibration conditions. Due allowance must be made for variations in the characteristics when the instrument is used in other conditions. The various static characteristics are defined in the following slides. The accuracy of an instrument is a measure of how close the output reading of the instrument is to the correct value. In practice, it is more usual to quote the inaccuracy or measurement uncertainty value rather than the accuracy value for an instrument. Inaccuracy or measurement uncertainty is the extent to which a reading might be wrong, and it is often quoted as a percentage of the full-scale reading of an instrument. So here's an example. A pressure gauge with a measurement range of 0 to 10 bar has a quoted inaccuracy of 1% of the full-scale reading. So 2 questions. What is the maximum measurement error expected for this instrument? And what is the likely measurement error expressed as a percentage of the output reading if this pressure gauge is measuring a pressure of 1 bar? The maximum error expected is 1% of the full-scale reading, which is 10 bar for this particular instrument. So hence, the maximum likely error is 1% of 10 bar, or 0.1 bar. So as worked out above, the magnitude of the error is 0.1 bar. So thus, when measuring a pressure of 1 bar, the maximum possible error of 0.1 is 10% of the measurement value. This example carries a very important message. Since the maximum measurement error in an instrument is usually related to the full-scale reading of the instrument, measuring quantities that are substantially less than the full-scale reading means that the possible measurement error is amplified. For this reason, it is an important system design rule that instruments are chosen such that their range is appropriate to the spread of values being measured, so that the best possible accuracy is maintained in instrument readings. Clearly, if we are measuring pressures with expected values between 0 and 1 bar, we would not use an instrument with a measurement range of 0 to 10 bar. Precision is a term that describes an instrument's degree of freedom from random errors. If a large number of readings are taken of the same quantity by a high precision instrument, then the spread of readings will be very small. Precision is often, though incorrectly, confused with accuracy. High precision does not imply anything about measurement accuracy. A high precision instrument may have a low accuracy. Low accuracy measurements from a high precision instrument are normally caused by a bias in the measurement, which is removable by recalibration. The terms repeatability and reproducibility mean approximately the same but are applied in different contexts. Repeatability describes the closeness of output readings when the same input is applied repetitively over a short period of time. With the same measurement conditions, same instrument and observer, same location, and same conditions of use maintained throughout. Reproducibility describes the closeness of output readings for the same input when there are changes in the method of measurement, observer, measuring instrument, location, conditions of use, and time of measurement. Both terms thus describe the spread of output readings for the same input. The spread is referred to as repeatability if the measurement conditions are constant, and as reproducibility if the measurement conditions vary. The degree of repeatability or reproducibility in measurements from an instrument is an alternative way of expressing its precision. So let's take an example. The width of a room is measured 10 times by an ultrasonic rule, and the following measurements are obtained, and you can see these here. The width of the room is then measured by a calibrated steel tape that gives a reading of 5.374 meters, which can be taken as the correct value for the width of the room. What is the measurement precision of the ultrasonic rule, and what is the maximum measurement inaccuracy of the ultrasonic rule? So the mean average, or the average value of the 10 measurements made with the ultrasonic rule, is 5.380 meters. The maximum deviation below this mean is minus 0.003 meters, and the maximum deviation above the mean is plus 0.003. Thus, the precision of an ultrasonic rule can be expressed as plus or minus 0.003 meters or 3 millimeters. The correct value of the room width has been measured as 5.374 meters by the calibrated steel rule. All ultrasonic rule measurements are above this, with the largest value being 5.383. The last measurement is the one that exhibits the largest measurement error. It is calculated as 5.383 minus 5.374, which equals 0.009 meters or 9 millimeters. Thus, the maximum measurement inaccuracy can be expressed as 9 millimeters. This example illustrates quite nicely that although the ultrasonic rule has fairly high precision, its actual measurement inaccuracy is substantially inferior. The degree of repeatability or reproducibility in measurements from an instrument is an alternative way of expressing its precision. This slide shows the results of tests on 3 individual robots that were programmed to place components at a particular point on a table. The target point was at the center of the concentric circles shown here, and the black dots represent the points where the robot actually deposited components on each attempt. Both the accuracy and the precision of Robot 1 is shown to be low. Robot 2 consistently puts the components down at approximately the same place, but at the wrong point. Therefore, it has high precision, but low accuracy. Finally, Robot 3 has high precision and high accuracy because it consistently places the component at the correct target position. Tolerance is a term that is closely related to accuracy and defines the maximum error that is expected in some value. While it is not, strictly speaking, a static characteristic of measuring instruments, it is mentioned here because the accuracy of some instruments is sometimes quoted as a tolerance value. When used correctly, tolerance describes the maximum deviation of a manufactured component from some specified value. For instance, crankshafts are machined with a diameter tolerance quoted as so many microns. And electrical circuit components, such as resistors, have tolerances, maybe 5%. The range or span of an instrument defines the minimum and maximum values of a quantity that the instrument is designed to measure. A particular micrometer is designed to measure dimensions between 50 and 75 millimeters. What is its measurement range? Well, it's simply the difference between the maximum and minimum measurements. Therefore, in this case, the range is 75 minus 50, or 25 millimeters. If the input to an instrument is gradually increased from 0, the input will have to reach a certain minimum level before the change in the instrument's output reading is of a large enough magnitude to be detectable. This minimum level of input is known as the threshold of an instrument. Manufacturers vary in the way that they specify the threshold for instruments. Some quote absolute values, where others quote threshold as a percentage of full-scale readings. As an illustration, a car speedometer typically has a threshold of about 15 miles an hour. This means that if the vehicle starts from rest and accelerates, no output reading is observed on that speedometer until the speed reaches 15 miles an hour. When an instrument is showing a particular output reading, there is a lower limit on the magnitude of the change in the input measured quantity that produces an observable change in the instrument output. Like threshold, resolution is sometimes specified as an absolute value and sometimes as a percentage of the full-scale deflection. One of the major factors influencing the resolution of an instrument is how finely its output scale is divided into subdivisions. Using a car speedometer as an example, and I'm talking about an analog one. Most of them are digital, but think of an analog one. This has subdivisions of typically 10 miles an hour. This means that the needle is between the scale mark. When the needle is between the scale markings, we cannot estimate the speed more accurately than to the nearest 5 miles per hour. This 5 miles per hour thus represents the resolution of the instrument. It is normally desirable that the output reading of an instrument is linearly proportional to the quantity being measured. The X's marked on this plot show the typical output readings of an instrument when a sequence of input quantities are applied to it. Normal procedure is to draw a good fit straight line through the X's as shown here. This can be done pretty accurately by eye, but is always preferable to apply a mathematical technique such as least squared line fitting. The nonlinearity is thus defined as the maximum deviation of any of the output readings marked X from this straight line. Nonlinearity is usually expressed as a percentage of full scale readings. So you can see it's the maximum deviation from the linear line that gives you the maximum nonlinearity. Suppose that the instrument characteristic shown here is that of a pressure sensor, where the input units are expressed in bars from 1 to 9 bars, and the outputs units are expressed in voltages from 1 to 13. What is the maximum nonlinearity expressed as a percentage of the full scale deflection? And what is the resolution of the sensor as determined by the instrument characteristic given? Well, the maximum nonlinearity is the maximum deviation of any data point away from the straight line through the data points. This is shown by the thick line here. The length of this line is 0.5 units, which translates to 0.5 volts. The full scale deflection is 13 units, which translates to 13 volts. The maximum nonlinearity can therefore be expressed as 0.5 over 13 times 100, or 3.8% of the full scale deflection. The resolution of the sensor is determined from the graph. It is the smallest change in input that is detectable. For the graph paper illustrated, the naked eye cannot determine anything smaller than one of the small squares, which is 1/10 of a unit, or 0.1 bar. This figure of 0.1 bar pressure is therefore the resolution of the sensor as determined from the graph. The sensitivity of measurement is a measure of the change in instrument output that occurs when the quantity being measured changes by a given amount. Thus, sensitivity is the ratio of scale deflection to the value of the measurand producing deflection. The sensitivity of measurement is therefore the slope of the straight line shown here. If, for example, a pressure of 2 bar produces a deflection of 10 degrees in a pressure transducer, the sensitivity of the instrument is 10 over 2, or 5 degrees per bar. All calibrations and specifications of an instrument are only valid under controlled conditions of temperature, pressure, etc. These standard ambient conditions are usually defined in the instrument specification. As variations occur in the ambient temperature, etc., certain static instrument characteristics change, and the sensitivity to disturbance is a measure of the magnitude of this change. Such environmental changes affect instruments in 2 main ways, known as zero drift and sensitivity drift. Zero drift is sometimes known by the alternate name bias. So zero drift or bias describes the effect where the zero reading of an instrument is modified by a change in ambient conditions. This causes a constant error that exists over the full range of measurement of the instrument. The mechanical form of bathroom scale is a common example of an instrument that is prone to zero drift. It is quite usual to find that there is a reading of perhaps 1 kilogram with no one standing on the scale. If someone of known weight 70 kilogram were to get on the scale, the reading would be 71 kilograms. And if someone of known weight 100 kilogram were to get on the scale, the reading would be 101 kilogram. Zero drift is normally removable by calibration. In the case of the bathroom scale just described, a thumb wheel is usually provided that can be turned until the reading is zero with the scale unloaded, thus removing the zero drift or bias. The typical unit by which such zero drift is measured is volts per degree C. This is often called the zero drift coefficient related to the temperature change. If the characteristic of an instrument is sensitive to several environmental parameters, then it will have a zero drift coefficient, one for each environmental parameter. A typical change in the output characteristic of a pressure gauge subject to zero drift is shown here. Sensitivity drift, also known as scale factor drift, defines the amount by which an instrument's sensitivity of measurement varies as ambient conditions change. It is quantified by sensitivity drift coefficients that define how much drift there is for a unit change in each environmental parameter that the instrument characteristics are sensitive to. Many components within an instrument are affected by environmental fluctuations such as temperature changes. For instance, the modulus of elasticity of a spring is temperature dependent. This figure shows that what effect sensitivity drift can have on the output characteristics of an instrument. Sensitivity drift is measured in the units of the form, in this case angular degree per bar per degree C. If an instrument suffers both zero drift and sensitivity drift at the same time, then the typical modifications of the output characteristics are shown here. This figure illustrates the output characteristics of an instrument that exhibits hysteresis. If the input measured quantity to the instrument is steadily increased from a negative value, this lower curve, the output reading varies in the manner shown in this curve A. If the input variable is then steadily decreased, the output follows the manner as shown in curve B. So this is increasing the measured variable, and then as the measured variable is released or removed, it follows a different path. This non-coincidence between these loading and unloading curves is known as hysteresis. Two quantities are defined, maximum input hysteresis and maximum output hysteresis, as shown here. These are normally expressed as a percentage of the full-scale input or output readings, respectively. Hysteresis is most commonly found in instruments that contain springs, such as the passive pressure gauge and the Prony brake, which is used for measuring torque. It is also evident when friction forces in a system have different magnitudes depending upon the direction of movement, such as the pendulum scale mass measuring device. Devices like the mechanical flyball, a device for measuring rotational velocity, suffer hysteresis from both of the above sources because they have friction in moving parts and also contain a spring. Hysteresis can also occur in instruments that contain electrical windings formed around an iron core due to magnetic hysteresis in the iron. This occurs in devices like the variable inductance displacement transducer and the linear variable differential transformer, also known as an LVDT, and the rotary differential transformer. Dead space is defined as the range of different input values over which there is no change in the output value. Any instrument that exhibits hysteresis also displays dead space. Some instruments that do not suffer from any significant hysteresis can still exhibit a dead space in their output characteristics. Backlash in gears is a typical cause of dead space and results in these sort of instrument output characteristics shown here. Backlash is commonly experienced in gear sets used to convert between translational and rotational motion. The static characteristics of measurement instruments are concerned only with the steady state reading that the instrument settles down to, such as the accuracy of the reading, etc. The dynamic characteristics of a measuring instrument describe its behavior between the time a measured quantity changes value and the time when the instrument output attains a steady value in response. As with static characteristics, any values for dynamic characteristics quoted in instrument data sheets only apply when the instrument is used under specified environmental conditions. Outside these calibration conditions, some variation in the dynamic parameters can be expected. The foregoing discussion has described the static and dynamic characteristics of measurement instruments. However, an important qualification that has been omitted is that an instrument only conforms to stated static and dynamic patterns of behavior after it has been calibrated. It can normally be assumed that a new instrument will have been calibrated when it is obtained from an instrument manufacturer and will therefore initially behave according to the characteristics stated in the specifications. During use, however, its behavior will gradually diverge from the stated specification for a variety of reasons. Such reasons include mechanical wear, the effects of dirt, dust, fumes, and chemicals on the operating environment. The rate of divergence from standard specification varies according to the type of instrument, the frequency of use, and the severity of the operating conditions. However, there will come a time, determined by practical knowledge, when the characteristics of the instrument will have drifted from the standard specification by an unacceptable amount. When this situation is reached, it is necessary to recalibrate the instrument back to the standard specifications. Such calibration is performed by adjusting the instrument at each point in its output range until its output readings are the same as those of a second standard instrument to which the same inputs are applied. The second instrument is one kept solely for calibration purposes, whose specifications are accurately known. The lecture started off by reviewing various different classes of instruments and considering how these differences affect their typical usage. We saw, for example, that null-type instruments are favored for calibration duties because of their superior accuracy, whereas deflection-type instruments were easier to use for routine measurements. We also looked at the distinction between active and passive instruments, analog and digital instruments, indicators, and signal output type instruments. Following this, we went on to look at the various static characteristics of instruments. These define the quality of measurements when an instrument output has settled to a steady reading. Several important lessons arose out of this coverage. In particular, we saw the important distinction between accuracy and precision, which are awfully incorrectly equated as meaning the same thing. We saw that high precision does not promise anything at all about measurement accuracy, and in fact, a high precision instrument can sometimes give very poor measurement accuracy. The final topic we covered was the dynamic characteristics of instruments. Clearly, the frequency of repeated measurements is limited by the time taken by the instruments to settle to a steady state reading. Thank you for listening, and see you in cyberspace.